This is the fifth video in a series covering abstract linear algebra. And this is the last video before we start looking at the structures that are typically studied in a linear algebra class. Like I've said before, these first 5 videos are to build some sort of intuition for dealing with things abstractly, which is how we will approach vectors, vector spaces, so on and so forth, which are the typical objects of study in linear algebra. So today we want to look at the notion of a ring. So a ring with unity, although there are rings without unity, but you'll study those in a dedicated abstract algebra course. Okay, so anyway, a ring with unity is a set R together with 2 operations. One of those operations you can think of as addition, and the other one is like multiplication. Here I'll use star for multiplication, but often I'll just write the 2 things next to each other as I have down here. And then furthermore, if you just look at R with the operation plus, this is an abelian group and the identity is 0. So you really just think of this as like an additive group. We've seen lots of additive groups in the previous videos. Next, R with the multiplication operation is a monoid with identity 1. So let's recall what a monoid is. It's a set with an operation that is associative and we have an identity, but we need not have inverses. So it's like almost a group, but we just don't have inverses for all of the elements. Furthermore, we've got this nice distributive property between the addition and multiplication. So A times B plus C must be equal to AB plus AC, and then A plus B times C must be equal to AC plus BC. So these are the 3 properties that a ring must satisfy. This abelian group with the plus, this monoid with the times, and then this distributive rule for the interaction of the plus and the times. Now furthermore, if the times multiplication is commutative, we would say that R is a commutative ring. Or maybe more specifically, R is a commutative ring with 1. 1 is the unit element. Okay, so let's look at some examples. This won't be all of the examples we look at, but this will be the ones that we start with. So the first kind of basic examples are just rings of numbers. So we've got integers, rational numbers, real numbers, and complex numbers. So you can clearly add those and form a group. And you can also multiply those and they clearly form a monoid. And then we've got a distributive rule which we learn in grade school. So in other words, addition and multiplication of numbers satisfies these conditions down here. Also, they're commutative because the multiplication is commutative. So this is in fact a commutative ring with 1. In other words, all 4 of these are commutative rings with 1. If you want to think about an example of a commutative ring that does not have an identity element, you could think of like maybe a little bit of a generalization of z, which is 2z. In other words, all even integers. So notice 1 is not an element of that. And in fact, there is no additive or multiplicative identity in this set, but it satisfies all of the other conditions over here. Okay, so now let's bump up a little bit. Let's look at z adjoint x, q adjoint x, r adjoint x, and c adjoint x. So these are polynomials with coefficients in z, q, r, or c, respectively. And we can endow these 4 sets with a ring structure 2 different ways, probably more than 2 different ways, but we'll look at 2 different ways. The first is with what I'll just call regular addition. So just add 2 polynomials together. And then regular polynomial multiplication. So that would be just multiply 2 polynomials together. So that will clearly give us a commutative ring. And we also have a unity element. We have a 1, which is just the constant polynomial 1, which exists in all of these for sure. But we could endow it with a different structure where addition is just regular addition of polynomials and composition is the multiplication. So instead of our multiplication being the product of 2 polynomials, it's the composition of 2 polynomials. So let's maybe do a little bit of an example based on this to show that it is not commutative. So let's notice if we take f of x to be x squared and g of x to be equal to 2x plus 1, thinking about these as being inside z adjoint x. And now let's look at f composed with g of x versus g composed with f of x. So here we're taking composition to play the role of multiplication. So notice f composed with g is exactly 2x plus 1 quantity squared, but that is equal to 4x squared plus 4x plus 1 if we were to multiply that out. Whereas g composed with f is equal to 2x squared plus 1. But these guys are clearly not equal to each other, so we have some sort of non-commutative element inside of this structure here. So here, this is a nice example of a non-commutative ring. It still has an identity, it's just in this case, the identity is not the number 1, it is the identity function. So here, that's the function, maybe I'll call it idx, which takes x to x. So if you compose that with anything here, you'll definitely not change it. So that would play the role of the identity function. Okay, so let's get rid of this and we're going to look at a couple of more examples. So another really important class of rings is the set Zn, the integers modulo n, where if you recall before, we looked at that as an additive group where we added two elements, divided by n, and then kept the remainder. Well, we could also define a multiplication operation the same way. There's a little bit to check there to show that it's well defined. We won't do that, we'll just take that on faith. But the operation is essentially the same. You take two elements, you multiply them, divide by n, and keep the remainder. So let's see, for example, in Z12, if we took 7 times 7, that's equal to 14, which is equal to 2, because we divide 14 by 12 and get a remainder of 2. Whereas if we do something like 6 times 6, we'll get 36, which is equal to 0, which is actually pretty interesting because we took two elements here that were not equal to 0, multiplied them, and got something that was equal to 0. And let's just really point out here that we're working in Z12. So this is obviously not true in the integers. It's true in the integers modulo 12. Okay, so let's take a couple of small values of n and compute full addition and multiplication tables for every element in each of these sets. So let's start with Z4. So the addition table is pretty easy. 0 is the additive identity so that we can just copy these down. 0, 1, 2, 3. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4, but that's equal to 0. Then 2 plus 1 is 3. 3 plus 1 is 4 again, which is 0. Now 2 plus 2 is 4, which is 0. 2 plus 3 is 5, which is 1. And then 3 plus 3 is 6, which is 2. And then we get another 1 here. So that would be a completed addition table for the elements of Z4. Recall, this forms a group under the addition, an abelian group. Now let's look at this. So if we multiply anything by 0, we'll get 0. So here we have an entire row and column of zeros. If we multiply anything by 1, we'll get 1. That's our identity here. So here we'll have 1, 2, 3, and then 2, 3. Now we just have to figure out what that 4 by 4 or that 2 by 2 square is. So 2 times 2 is 4, which is 0. So that's kind of interesting in itself that we multiply two non-zero things and get something 0 again. In class, we'll talk about this a little bit more deeply. Now let's look at 2 times 3, that's 6. But if you divide by 4 and keep the remainder, you'll get 2. So that means we have a 2 here and a here. Now 3 times 3 is 9. Divide by 4 and keep the remainder, you will get 1. So that means the multiplicative inverse of 3 is itself. So actually, let's note that. Some weird things are going on here. We have 2 times 2 is equal to 0. And this is all in Z4. But 2 times 3 is equal to 2, and 3 times 3 is equal to 1. So this says that 3 has a multiplicative inverse, a path back to the multiplicative identity. But notice 2 does not have a path back to the multiplicative identity. And we can see that just by looking at this row. The only thing we can achieve by multiplying by 2 is 0 or 2. Now let's go ahead and do a chart for Z5 as well. So the addition will go quickly. We'll have 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Add 1, we'll get 2, 3, 4, 0. Because 1 plus 4 is 5. That has a remainder of 0. And then here we have 3, 4, 5, which is 0. Okay, now adding 2, we'll get 4, 5, which is 0, and then 6, which is 1. Same thing down this way, 0 and 1. Add 3, 3 plus 3 is 6, which is 1. 3 plus 4 is 7, which is 2. So we can fill that in. 4 plus 4 is 8, which is 3. So that's a filled in addition table for Z5. Like I said before, this forms a group, an abelian group under addition. Now let's look at the multiplication table. So the 0 row and column is not super interesting. We just get a bunch of zeros. But let's see what happens for everything else. The 1 row and column is also pretty easy because that's the multiplicative identity. So we get 1, 2, 3, 4, 1, 2, 3, 4. Now let's see, 2 times 2 is 4. 2 times 3 is 6, which is 1 because we're working mod 5 now. 2 times 4 is 8, but 8 is 3 because we're working mod 5. Now this is going to be 1, 3 as well because we have commutativity. Now 3 times 3 is 9, but that's 4 because it has a remainder of 4 when divided by 5. So we have 4 here, and then 3 times 4 is 12, which is 2, 2. And then finally 4 times 4 is 16. Divide that by 5, keep the remainder, we get a remainder of 1. But now something a little bit interesting is happening over here. We notice that everything that is not equal to 0 has an inverse. So let's write that over here. So in Z5, we have the following facts. 1 times 1 is equal to 1. So 1 is its own inverse. 2 times 3 is equal to 1. So that means 2 and 3 are inverse pairs of each other. And then finally, 4 times 4 is equal to 1, so 4 is its own inverse. So in other words, everything that is not equal to 0 is invertible. And when I say invertible, I mean invertible with respect to the multiplication operation. And in fact, commutative rings that have this property form a very important class of rings, which we're about to talk about. So that leads us into the following definition, a field lowercase k. So I'm not really sure where the notation of using a lowercase k for a field comes from, but it's quite typical. Maybe if you know, post in the comments. So anyway, a field k is a commutative ring where k times, that's how I read that, which is k except for the additive identity 0, forms an abelian group. Let's notice that means that every non-zero element has a multiplicative inverse. Well, remember, being an abelian group means that everything has an inverse, and that invertibility is the only thing that's lacking from it being a monoid in the first place. Okay, so let's look at some examples. So maybe the most important examples that we'll work on in the future will be Q, the rational numbers, R, the real numbers, and C, the complex numbers. So it's pretty clear if we've got a non-zero element of Q or R, then it's invertible just by its reciprocal. For example, like x times 1 over x is equal to 1. Same thing for a complex number. Let's maybe note that if we take a plus b, we can find its inverse by multiplying by a minus bi over a squared plus b squared. So I'll let you guys check that if you multiply this guy with a plus bi, then you'll in fact get the number 1. And this is possible as long as a squared plus b squared is not equal to 0, but that's possible as long as the whole thing is not identically 0. Then on the last board, we saw that Z5 formed a field because every non-zero element had a multiplicative inverse. Well, it turns out that Generally, when we're talking about fields, we don't use this Z underscore notation, we use an F underscore notation. So generally, like I said, in the setting of fields, we would write this as F5. So it's the finite field with 5 elements. So actually, in general, for any prime number, P, so I'll call it P, the set FP, which is the same thing as the set ZP, so the integers modulo P, is a field. And then in this case, it has P elements. Now, if you have N here, which is not prime, it is not a field. And we can check that really quick. So let's say we have Zn with N equals to A times B. So that's a factorization of A times B, where A and B are both not equal to 1. So it's like a non-trivial factorization of N. So let's notice that A and B are both in Zn, and they're both not equal to 0. I guess I should put here that they're also not equal to 0. But A times B is N, which is equal to 0 in Zn. But the fact that those multiply to something equal to 0 tells you that, in fact, they do not have inverses. There's a little bit more work to do, but again, we'll save that for like a proper abstract algebra course. Okay, so the takeaway here is that maybe the 4 classes of very important fields that we want to work with, or maybe the 2 classes, are just the standard numbers, like rational numbers, real numbers, and complex numbers, and the finite fields with P elements. So these are the integers modulo P, where we have addition and multiplication, where we divide by P and keep the remainder. So let's actually work through one of these examples real quick. Let's look at maybe F7, since we already looked at F5, just to get a feel for it. So let's get a multiplication chart for this on the board. Okay, so now we've got our multiplication chart for F7. So in other words, the integers modulo 7. So that means we need to multiply everything between 0 and 6, divide by 7, and keep the remainder. So what's happening in the 0 row and column is super boring. We just get 0 in all of those cases. In fact, we don't really need to look at the 0 row and column, because what we really need to ensure is that everything that is non-zero has an inverse. That's what would make F7 a field. So let's look at the identity. So we've got 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. So that's the completion of multiplication by 1. Now let's look at 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. But working mod 7, that is equal to 1. So let's maybe put a circle around this and this to show we've come up with an inverse pair. So the inverse pair for 1 is 1 times 1 is 1. The inverse pair for 2 is 2 times 4 is 1. Now let's look. 2 times 5 is 10, but keep dividing by 7 and keeping the remainder, we get a 3. 2 times 6 is 12, we get a 5 there. Now we can use symmetry to fill in the 2 column. We have 6, 1, 3, 5. Now let's work with 3. So 3 times 3 is 9, which will be 2 in F7. 3 times 4 is 12, which is 5 in F7. 3 times 5 is 15, but 15 is 1 more than 14, so this makes 1. So there we've got another inverse relationship. 3 and 5 are multiplicative inverses. Then 3 times 6, well, let's see, 3 times 6 is 18, which will be equal to 4. Now, again, we can use symmetry to fill this in, 5, 1, 4. Now let's look at 4. So 4 times 4 is 16, which is 2. 4 times 5 is 20, which is 6. And 4 times 6 is 24, which is 3. Use symmetry to fill in the rest. We only have symmetry because of the commutativity here, just by the way. If we were in a non-commutative ring, we could not use symmetry to fill in the bottom half. Okay, so now 5 times 5 is 25. Let's see, 25 will be 4. 5 times 6 is 30. But let's see, 30 will be equal to 2. So we get a 2 here. Now 6 times 6 is 36. That's 1 more than 35. So that means it has a remainder of 1 when dividing by 7. And that's our last inverse pair. So let's note we have 1 times 1 is equal to 1, 6 times 6 is equal to 1, and then 2 times 4 is equal to 1, and 3 times 5 is equal to 1. So there are the inverse pairs for all of our non-zero elements in F7, really checking for sure that this forms a field. Okay, so let's get rid of this and then we'll prove some standard general results involving rings. So we'll finish off with a simple general result involving rings and then some warm-up exercises. So let's suppose that we have a ring R, and it has a multiplicative identity 1 and arbitrary elements R and S. Before I look at the statements here, I want to make the following remark. By negative R, I mean the additive inverse of R. So in other words, we have R plus negative R is equal to 0. But we often read that as R minus R, just kind of FYI. And I point that out because some of these deal with the subtle difference between additive inverses and multiplying by -1. Okay, so anyway, let's look at this first one. It says 0 times R is equal to R times 0, which is equal to 0. So in number rings, we know that multiplication by 0 clearly gives us 0. We've known that for many, many years. But we want to show that that happens in a general ring. So in other words, multiplying by the additive identity will always give us 0. Okay, so let's maybe see how we can do that. So let's start with this. We have 0 times R, and notice that is the same thing as 0 plus 0 times R, because 0 is the same thing as 0 plus 0. But now using the distributive rule, that gives us 0 times R plus 0 times R. But now we can use cancellation and the group law to cancel this side with this side. But what we're left with on this side is just 0. Maybe if you wanted to, you could rewrite this as 0 plus. So in the end, we've got 0 equals 0 times R. And that's really just proving this is equal to this. For the other one, I'll leave that to you. You do essentially the same sort of calculation. Okay, let's move on to the second one. That says that R times the additive inverse of S is the same thing as the additive inverse of R times S. Okay, so let's see how we can do that. So let's look at the object RS plus R times negative S. So hopefully we'll get 0 for that and we will have our result, but we don't have that yet. So let's use our left distributive rule to bring the R out. That'll leave us with R and then S plus negative S. But then we know S plus negative S is 0. So we have R times 0, but R times 0 is 0 from this first bit. So we're left with R times S plus R times negative S is equal to 0. We can subtract this side from both sides of our equation, and we're left with RS equals R times negative S. And then you could do this middle one is equal to the last one very, very similarly. Again, I'll leave that for you. Okay, so now let's move on to this one. Okay, so now moving on to this one, I'm first going to look at this object, minus R times minus S, and then minus RS. And so now our goal is to show that that is equal to 0. Well, let's rewrite that a little bit as minus R times minus S plus minus R times S. And I'm allowed to do that first step by this equation right here. Actually, the bit that we did not prove, but again, it follows similarly. And now we can factor a minus R from both sides of this. So doing that, we'll have minus R times minus S plus S, but that's equal to minus R times 0, which is equal to 0 from this first result. But now we've got this equals 0. We can add RS to both sides, and we're left with minus R times minus S equals RS as needed. And so now we're ready to move on to this last result. So we'll look at that by taking R plus minus 1 times R. So hopefully we'll get 0 for that. If we do, then we've again built an equation where we can manipulate it to get this result. Let's rewrite this maybe as 1 times r plus negative 1 times r, again, because we have an additive identity. And just to reiterate, we read this negative 1 as the additive inverse of the multiplicative identity. We can use right distributive rule here to write this as 1 plus negative 1 times r. 1 plus negative 1 is 0. We get 0 times r, which is 0. But again, we forged the correct equation. We subtract r from both sides, and we have minus 1 times r is equal to negative r, which proves this last result. Okay, great. So now let's finish off with some warm-up exercises. So I've got a couple of warm-up problems now. The first is to fill in the gaps from the last proof. So I think in the proof, I showed that 0 times r was equal to 0. So let's fill in the gap and show that r times 0 is also equal to 0. Furthermore, we showed that r times negative s was equal to negative rs. We'll now show that negative r times s is minus rs. And then I've got one more. So let's suppose that R is a ring where 0 is not equal to 1. So in other words, the additive identity is not the same as the multiplicative identity. There's actually a single ring where the additive identity is the multiplicative identity. Maybe for a bonus type question, think about which ring that is. Okay, so anyway, we've got a ring where 0 and 1 are different. And A and B are elements from this ring so that when you multiply them, you get 0. So what you want to show is that A and B cannot have multiplicative inverses. So here, let's maybe write down here that we definitely mean multiplicative inverses. So in other words, if you've got the product of two non-zero things, I should point out here that these are both non-zero. The product of two non-zero things equals 0, which, as we saw, is possible in some rings. Then it's impossible for those guys to have inverses. And that's a good place to stop.